Lesson 79, Volumes of Revolution. In the beginning of this lesson, before this video, I hope you have completed the investigation suggested and to discover that when you have a function drawn on the Cartesian plane and imagine that you are rotating the plane containing that function between either the x-axis and y-axis, between a certain interval, it will actually create a 3D shape. And integration will allow us to calculate the volume of these 3D solids of revolutions by considering that you're really adding up really thin disks, right? That have different radii, but the radii are defined by the distance between your function and the x-axis or y-axis. So in the diagrams here, on the left side, if you're forming a solid of revolution by rotating your function about the x-axis, then you are going to have to multiply pi by the integral of the square of the function and calculate its definite integral from the boundary a to b. If you have a volume of solid of revolution formed between a function f of x, and then by rotating it about the y-axis, like what's shown on the right here, you will first have to make sure your function is written as a function of x in terms of y, okay? Because you'll be integrating with respect to y. And then again, it's very similar to what you saw in the formula. It's pi r squared, right? All sum up together. So it's like pi x squared, integral from a to b dy. So let's take a look at our first example. Example 1. Find the volume of the solid formed when the graph of the curve y equals to the square root of x minus 1 in the interval 1 to 5 for x is rotated to pi radius about part A, the x-axis, okay? So what does this graph look like? Well, I know that it is this function starting at 1. Because of the minus 1, we shift it over to the right. Okay, and then it's going to end at 5 on the x-axis, like that. So using the formula, the volume is pi from 1 to 5 of this function squared dx. Simple enough. We have pi from 1 to 5 x minus 1 dx, which implies I have x squared over 2 minus x from 1 to 5. And what have we got here? 5 squared, 25 over 2 minus 5 minus 1 over 2 plus 1. Okay, simplifying this, 25 over 2 minus 1/2 is 24 over 2, 12. 13 minus 5 is 8. So 8 pi cubic units. Okay. But what about now in part B? We're going to find the volume of this solid of revolution if I actually rotate this curve along the y-axis. Well, first thing we need to remember is that now we need a function of x in terms of y. So isolating x from the original function, I get x equals to y squared plus 1. That's the first main point. Secondly, the interval 1 to 5 is for x. So now we need to change our interval of integration for the y variable. So we can use the graph here. When x is equal to 1, y is equal to 0. What about when x is equal to 5? 5 minus 1 is 4, so this is 2. Okay? So now we're ready. this particular volume will be pi times the integral from 0 to 2 of y squared plus 1 squared dy. We can expand the brackets because it's easier to integrate. Y to the 4 plus 2y squared plus 1 dy. This gives me 5 plus y cubed, so 2y cubed over 3 plus y from 0 to 2. And so let's sub. I know that the second term will all be 0, so that's easier. Here, I have 2 to the power 5, 32 2 over 5 plus 2 times 8 is 16 over 3 plus 2. Okay, so doing some mental math, or use your calculator if you have it, if you're allowed to use it. It should be 206 pi over 15. And this is cubic units. Okay. Here is example 2. Find the volume of the solid of revolution generated by rotating the region bounded by the graph of y equals arc sine x and the lines x equals to 1 and y equals to 0 through 2 pi radians about the y-axis. So here we know that we're going to be rotating in this direction, which means that I must have a function of x in terms of y, and also I need to know my boundaries when y is equal to 0. So I got my first boundary, but then I'm given the line x equals to 1. But theoretically speaking, I should be looking for the corresponding y value. Okay, so we're taking this plane here and rotating it about the y-axis. Okay, so there are a few things that we have to do before we apply the volume formula. First, I have y equals to arc sine x, meaning that sine of y is equal to x. Okay, and so here is my first function, and then I also need to know my cutoff point, right, for the integration interval. So when x is equal to 1, I have sine y equals to 1, and then y must be pi over 2, because the graph also shows that, you know, that is the range of this arcsine function. Okay. Now, here is the work for calculating volume. So pi times 0 to pi over 2 of the square of this function, so sine square y dy. Does this look familiar to you? Like, do we have a rule that will allow us to integrate the square of sine y? If you recall, we have done an example before that asked us to integrate the square of cosine y or cosine x. I don't remember x or y. What did we do back then? Back then, I remember screen, we had to rely on a trig identity. This time, we will also use that trig identity, but instead of writing it as cos square y, we need this in terms of sine square y. And it's this guy. Okay? If I know that cos 2y is 1 minus 2 sine square y, then what must sine square y be? It must be 1 minus cos 2y over 2. Yep. And so using this substitution, we can continue to do this. So pi over 2, 0. We have 1 over 2 minus cos 2y over 2 dy. I just break it up into two terms. And then the first term, 1 over 2, integral is half y. The second term, I have cos 2y becomes sine 2y over 2, so over 4. And this is pi over 2 and 0. Okay. This way, I will have pi multiplied by pi over 2 times a half, pi over 4, minus sine pi over 2 times 2, so sine of pi, which is 0, so that's good. And then minus 0 times half, minus sine of 2 times 0 is also 0. That's good. That means this volume is going to be pi squared over 4 units cubed. Okay. Here is example 3. Find the volume of the solid form by rotating the region enclosed by the curves of the graphs of y equals the square root of x and y equals to e to the power of 3x minus 12 plus 1 through 2 pi radians about the x-axis in the first quadrant. So it's good to visualize what's going on here because we're talking about a region enclosed by two graphs. Using my pen, I know that we're talking about this region and we're going to take it around the x-axis. Okay. Intuitively, you probably know that, well, in order to do this question, I need to know, the boundaries of my solid of revolution. Using graphing calculator or from this graph, you can tell that, this point is at 1 and 1. And then the end point is at 4 and 2. Okay, so we have got our boundary set. And then there will be a hollow section because there is nothing here, right, under the red graph. So in a sense, I can imagine this whole volume of solid of revolution will be constructed by first taking the whole solid formed by the blue curve, which is square root of x, and then let's call this f, and then take away the volume, the hollow volume that we have shaded in between g of x and x-axis, okay, in that region that we're talking about. So let's put this to work. I have pi from 1 to 4, okay, the square of f of x minus the square of g of x. Like that. So it just becomes algebra here. And I just use a graphing calculator because it will help you to evaluate your definite integral. Don't forget to multiply pi at the end. You should get roughly 11.5 if you round to 3 significant figures. Okay. And then if I'm interested in finding the volume of revolution formed by that shaded piece, but now this time about the y-axis, I just have to make some slight changes to the functions themselves, right? And then apply the same idea. And this time we are going from 1 to 2, okay, as our boundary of calculations for the calculations. All right, so let's write on the side maybe So if I have y equals to square root of x, then the function should be x equals to y squared. And if I have, what was it? It's y equals e to the power of 3x minus 12 plus 1. What is this in terms of x? So I have y minus 1 equals to e to the power of 3x minus 12. So if I ln this, I get 3x minus 12, which means that x must be ln times y minus 1 plus 12 over 3. Okay. We will be doing this using the graphing calculator, so I'm not too worried about this function being too complicated. So here I have pi. This time we set. We're going from, let's see, 1 to 2. Okay. The outside function in this case is actually the ln function. Okay, so ln y minus 1 plus 12 over 3 squared minus the square of the second function. So this squared. Okay, and then using your graphing calculator, this works out to 23.1 cubic units. That's it.